So I'm going to describe some work I've been doing with Michael Spanofsky and Nick Chancellor. In these two papers, the work has appeared, and our interest is in using quantum annealers as a kind of laboratory to study quantum theory. So it's quantum field theories, quantum mechanics. And this is what we achieve, or what we aim to achieve. We set up and study a quantum annealer as a laboratory for complicated quantum systems. The particular things we're interested in are things that involve tunneling dynamics. So these are systems where it will get stuck for a long time and then tunnel into a different state. And so that sort of dynamics is what we're interested in observing. And a quantum annealer is uniquely suited for this task, I will argue. It outperforms any classical simulation, but also it's much better suited than say a quantum gate computer. It's almost ideal for this sort of task. So this is us. So on the left is myself and Michael, and we're in the Institute for Particle Physics Phenomenology. It's one of the world's largest particle theory groups, and we liaise with Nick Chancellor in the quantum computing group, and so that's where we started developing these things. These are the sorts of problems that we might be interested eventually in looking at, the sorts of physics problems. So why are these things interesting, these sorts of processes? So where you may observe tunneling in certain manifestations of what's called the Higgs mechanism, which you've probably heard of, there's inflation, sort of cosmological scenarios, baryogenesis, creation of matter-antimatter asymmetry, and anything involving an instanton, what we call instanton processes. So that occurs whenever I have a potential like this, and I get stuck in a local minimum here, and I'll sit there for a long time in a quantum mechanical system, and eventually I'll quantum tunnel through to the true global minimum, and that is what's called an instanton process, that sort of thing. It's described by what's called an instanton. So those are all of these tunneling processes, the sorts of things that we want to look at eventually. These are all hard to treat mathematically and hard to simulate on a classical computer, and also very few phenomena that involve tunneling have been observed experimentally. So those situations are very specific and unique, and they're not easy to observe. Our approach is to use the annealer to encode them physically. So we actually create the potential on the annealer, and we attempt to observe it tunneling. So what I'm going to describe is not really a simulation, it's a genuine quantum experiment that we're performing. We're observing genuine tunneling when we do this. So let me begin at the beginning by just describing what it is we want to look at. And we're going to look at a very specific situation, which is, of course, the easier thing to look at. It's just it's essentially the Schrodinger equation we're going to look at. So it's tunneling in a one-dimensional system. So it's described by a one-dimensional Schrodinger equation. Out of habit, I'm going to call the space coordinate phi instead, but think of it as x. It's a single space coordinate, phi. And so we have a potential for our Schrodinger equation, which looks like this. And I'm just going to take this as a specific, simple potential to look at. The reason I like the tanh squared sort of functions is it gives me a nice, well-behaved minima. I can move them around at will by adjusting this v. So you see here, v is 4. And I've got 2 minima, and also at large values of phi, of coordinate, it doesn't blow up, it just goes to 1. So it's all nicely behaved. So this is a kind of canonical potential we can look at and see what should happen. So let's just look at it, first of all, numerically, so we can always do that. So we want to observe this sort of behavior. We want to begin in the false minimum on the left and observe the system tunneling to the lower one on the right. So we want to begin by having a wave function that's localized in this minimum and see what happens to it. And we're going to do that. Of course, we have to solve the Schrodinger equation. So I'm just going to remind you what it looks like. So this is the Schrodinger equation, and the potential appears there, and it's u of phi, so phi is the space coordinate I'll just remind you. So we can evolve that on a laptop or something and see how it evolves. So I'm going to begin with a wave function that's localized in this minimum here, and this is the wave function at t equals 0, and I can evolve the Schrodinger equation numerically and see what happens, and after a while it looks like that. So it's a dynamical sort of process. The wave is kind of sloshing around a little bit, but generally what happens is it leaks into the second minimum like that. And a little bit later, it leaks a little bit more, and you see this peak will start to grow, and eventually everything will be over here in the new minimum, and that's how the theory decays. So that's the sort of thing we want to encode on the annealer, and in order to do it, we're going to begin with an observation from 1950, which is due to Feynman essentially. And that is the following. It says, so Feynman tells us that if I want to describe the Schrodinger equation, I can think of it as a zero-dimensional field theory. So that it's something which has got a kinetic term, and if you look at that, you can recognize that's just mv squared essentially. So it's a mv squared over 2. It's a non-relativistic kinetic term, and it has a potential. And I can think of this thing phi as a field. So if I assume that the annealer provides all the kinetics for us, then all we need to do is encode that potential, the u of phi, onto the annealer. And if the kinetic term looks like that, which is an assumption we have to make, but we're going to assume that, then it should behave as the Schrodinger equation does. So that's what we do. We're going to encode the potential u, and we're going to assume that the kinetic terms come for free on the annealer. So this is how we do it. The first thing we need to do is encode phi itself, and in order to do it, we are going to have to discretize its value, obviously, on the annealer, and we're going to use n qubits. So obviously you need n to be as large as possible, and then your phi, your continuous phi, is described as in a discrete way as phi 0 plus integer times xi. So xi is a small number. Phi 0 is a fiducial starting coordinate. And so, I don't know, some value -3 or something. So it goes from phi 0 to phi 0 plus n xi. That's your domain that you're going to be looking at. And so this value of phi, what we want to do is represent it on the spin chains in the annealer. And in order to do it, so this is where we first called on Nick. So Nick, Chancellor, has devised this, what's called domain wall encoding, in order to describe the continuous thing. So in order to describe it, what you want to do is to describe that thing, phi 0 plus j xi, in terms of a domain wall position on a single spin chain. So this position here, between all the minus spins on the left and all the plus spins on the right, is encoding the continuous field value. So in order to get the field value back from this thing, what you do is you use this equation, and if you look at this thing, you see that I'll have a contribution from everywhere on the left of the wall here, where all of the sigmas are negative, and that's going to give me a plus xi from each of these positions. On this side, I get nothing because the xi's because the sigmas are positive. So I recover this phi 0 plus j xi there. So that's how we want to extract our field value from a particular configuration of spins. And in order to do it, for it to make sense, we have to make sure that we encode it to avoid this sort of thing happening. Right? So we want to avoid the situation where we have more than one place where it goes from -1 to +1. And we do it by putting a particular sort of interaction onto the annealer. So this is where I need to remind you what it is that we're playing with on the annealer. It's this Ising model. So so for all of the spins, the different spins that appear in the Hamiltonian, we're allowed to choose interactions, quadratic ones, the j's, and the linear ones, the h's. And as well as that, there's this transverse field term, which is going to sort of make the thing start to have dynamics, essentially. So that's what we have to play with in order to make sure we avoid this sort of double, triple crossing thing. We can use this particular Hamiltonian. So we can begin with this Hamiltonian, and the idea of this Hamiltonian is it disfavors that sort of configuration. So if I show you, if I look at the individual terms here, the linear ones, the linear terms, they prefer to have the spins at different values at the two ends. So you see this one likes a negative sigma 1 and a positive sigma n. So this one is forced to be negative and this one is forced to be positive. On the other hand, these terms here, they don't like anywhere where it goes from minus to plus or plus to minus. So every time I have a wall going from minus to plus, I'm going to get a penalty from this term. And so it enforces a configuration where it's minus at the left, plus at the right, and just one single place in the middle, which we're calling the domain wall, where it goes from one to the other. So that's going to force our proper encoding of field values. Right, so that's the field setup, and then what we want to do is add a potential, which is actually quite simple to do, because all you need to do is to make sure you add a term which only contributes at the position of the domain wall. And so if you look at what this thing is, if you look at this set of linear terms, you see I'm going to get nothing where adjacent spins are the same value. I'm only going to get something where they have a different value. So I'll get just a contribution there at the domain wall, and then I multiply it by the potential there. So that's the u of phi 0 of the field value, phi 0 plus j psi. So if you look at that, this is actually equivalent to the derivative, the derivative du by dx at that point, du by d phi. Right. So that's so the potential just then ends up as a linear term on the annealer. So those H couplings. So, and that's all we do. So we add those things together into the Hamiltonian. As I said, we want to have a large number of n to make it as continuous as possible, a large number of qubits. So 200 is something which works pretty well, and so this is a kind of typical embedding that you might get on the annealer. Once you've added everything together, you end up with a chain that looks like that. So it's quite large on the annealer. Anyway, but it's relatively easy for it to be embedded. Just as a check, we can see what is being passed to the annealer. So we can look at the Ising model, and we can just extract the values of the Ising model for all those different spin configurations, which correspond to different phi's, and we indeed recover the right sort of potential. So that's our configuration. So now let's see what happens. So we put that onto the annealer, and we let it go for a certain amount of time, and this is what we observe. So compared to the numerical evolution, you see it's doing exactly what you would expect. In that this is really a counting experiment. So we are literally counting the number of outputs at certain values of phi, right? So certain spin configurations. We're just counting the spin configurations. But you see it's recovering the wave function that we expect. So it's leaking across to the new minimum with time. So as time goes on, so t is in microseconds. So as we increase t, you see that this peak does indeed increase, and the wave function that we are measuring is indeed moving across. Here you see we're taking v as 2.5. So this is where the new deeper minimum is. Okay, so that's the first thing you can check. It seems to behave as normal, as you'd expect. And as I emphasize, it's really an experiment that we're doing. So it's a counting experiment, just like the double slit is a counting experiment. We're just counting the number of points that we get at different values of phi. So we can also vary other parameters. So we can vary v. And what you expect, and you can calculate it analytically in one dimension. So there's an approximation which you may know, it's called the WKB approximation. But so that tells you that what should happen is that the rate of decay, so the rate that it tunnels through to the new minimum, goes down exponentially as v increases, as some function of v. And so we observe that as well. So this is for the same times at different values of v, and you see that as v increases, the decay really drops off exponentially fast with v, which is what you expect. And we can actually fit it to a curve. So this is what the WKB approximation should give you. It should give you the decay rate is gamma, and the theory tells you that the log of gamma should be linear in v, and so it's some constant times another constant minus v, and this is what we observe. You see, the numbers are not that far off from what you expect theoretically, and of course there are two constants, so you can always fit two of these points, but you see the rest of the points are lining up exactly as you expect. So it does seem to be behaving as we expect. There are other things you can do as well, which support the fact that this is quantum and not, for example, thermal excitation, which is the thing which you would worry about, that maybe this hopping across, this is actually hopping across and not really tunneling, it's thermal excitation. So that's something we can attempt to eliminate, and there's various tests that you can do. So here's a simple one. So suppose I don't have two minima, but I've just got one here. So I take the potential with just one minimum at 0, but I start the field at some value up the hill, so -2. And then what I can do is I can turn off the transverse field component. So that's the thing which is introducing the dynamics, it turns out. If I turn off the transverse field component, you find that there's no dynamics at all. It won't even roll down this hill. Won't roll down the hill at all. So in a sense, what the dynamics is really, you can think of it as a kind of sort of micro hopping, which is being driven by the transverse field component. And if we turn that off, even that doesn't operate. So there's no dynamics without the quantum mechanics, in effect. Okay, so you see that as you turn, so S is your anneal parameter. As you increase the quantumness of it, so I'm sort of dialing up the transverse field component, it does sort of slop down here more rapidly. So it starts to move dynamically. There's something else that you can do. I mean, if you study this a little bit more, to see that the dynamics is actually behaving as we expect. So here I'm again solving the Schrodinger equation, first of all on my laptop. And so I begin with a system which is at -2 and let it evolve. And you'll see that it doesn't actually, I mean, you might naively expect it to move as a single lump down to the minimum there. It doesn't actually do that. And if you solve the Schrodinger equation, it kind of slops across. So there's always a kind of minimum here between two maxima. It's like it's tunneling even when there's no barrier here. It's kind of behaving as if it's a tunneling, the way it slops down to the minimum. And so if you let the Schrodinger equation evolve, you'll see that a new minimum grows, a new peak grows at the minimum, and it kind of slops across, and you see here it goes a bit too far, and there's a peak appears in the middle, and so on. So we can see if that happens in the real case and in the annealer. And so in the annealer, we can look. So now let's look at a two-dimensional example. So I'll just show you that you can do that. So this is in 2 dimensions. You can also encode that. This is the potential we have we're putting on in 2 dimensions. And what we want is to see is the system begin here and just slosh down into the minimum and see how that behaves. And this is what it looks like. So you see that it's behaving pretty much as you expect the quantum system to behave. So if I just let it run a few times, you'll see it begins here at -2, and it rolls down the valley into the minimum. But you see it doesn't really, it's not a single lump. It grows this peak here, and it kind of sloshes across, just like it did in the numerical simulation. So I can also show you that. You can see it as a heat map where it's a little bit more obvious. It begins here, as a bright spot, and it appears there, another bright spot appears there, but the wave function kind of leaks across. It doesn't just go as a single lump. So it's all sort of pointing in the right direction, essentially, that it's really a genuine quantum process that's going on, and that we're really seeing quantum tunneling. So to conclude, we feel like we're on the start of a long journey into looking at these things. It looks possible to build quantum theories by hand. So essentially, any potential that you want to put onto the annealer, you can put it on and experimentally measure what happens to it. So measure the wave function, the time dependence of the wave function. So as an example, we believe we are observing and measuring tunneling out of false vacua, and it does look to be behaving in the correct way. So it's an interesting quantum lab, we think, for future tests of quantum mechanics and arbitrary quantum field theory. So there are many other processes that we would be interested in looking at, in particular field theories, early universe problems, and so on. And of course, then the other thing we would like to do is, of course, make more precise tests of this and sort of stronger verification and better support with different systems, by looking at different systems. Thank you.